Welcome to the third installment of a three-part video series where we're examining the infinite series where k goes from 2 to infinity of 1 over k times k minus 1. In the first part of the video series, we examined the series for convergence by applying the nth term test and the comparison test. In the second part, we used the integral test and the ratio test. And what we discovered in the first part, when we did the nth term test and when we did the ratio test in part 2, was that these two tests were inconclusive for determining convergence of the series. Whereas when we used the comparison test and the integral test, we were able to determine that the series converges. Now, there was one advantage in using the integral test over the comparison test, and that was that the integral test allowed us to come up with bounds for the size of the series. What we want to do now, though, is reconsider that question. We know that the series converges, but we want to examine the sequence of partial sums because perhaps we'll be able to find a formula for the sequence of partial sums and then examine the limit so we can determine the actual value to which the series converges. So as we reconsider this series, as before in parts 1 and 2, I've got the first few terms of the series written here, but you may recall from our work in the integral test that we were able to use a partial fraction decomposition to rewrite the general term of the series. So I've replicated the work for that here, but I'm not going to explain it. If you want to hear the full explanation, you can watch the video for the integral test, namely we set up our partial fraction decomposition, we multiply by the common denominator to clear the denominators, we pick appropriate values for k to help us find the a and the b, and we end up with this partial fraction decomposition that 1 over k times k minus 1 can be rewritten as 1 over k minus 1 minus 1 over k. So when we think about our series, we can take that general term and replace it with the partial fraction decomposition, and then we can start writing out terms for the series with this new version of writing the general term of the series. So when k is equal to 2, our first term for the series is 1 over 1 minus 1/2. Then we go to when k is equal to 3, and plugging 3 into this formula will give us a 1/2 minus a 1/3, so that becomes our second term of the series. And then we'll add our third term of the series, which is when k is equal to 4. That will be a 1/3 minus a 1/4, and then the fourth term of the series, when k is equal to 5, is equal to 1/4 minus 1/5. And when we look at this, we notice that because of the way it's written now, with some subtraction for embedded in each term, and then adding the individual terms, we're going to get some cancellation in there. And so this appears to be a telescoping series, which gives us hope that we might be able to come up with a formula for the sequence of partial sums so that we might take a limit and find the actual value of this series. So let's do that. So first, we're going to try to look at the sequence of partial sums and see if we can figure out a pattern that will allow us to state a formula for Sn, which is the sum of the first n terms of our series. S sub 2 is the sum of the first two terms of the series. So we have the 1 minus 1/2, which is the first term of the series. Then the second term of the series is the 1/2 minus 1/3. If we simplify that expression, we end up getting a 1 minus 1/3. Similarly, when we do S3, we have the sum of the first three terms of the series. If we write them all out, so the first one is when k is equal to 2, plus the term when k is equal to 3, plus the term when k is equal to 4. Again, we have lots of cancellation, and this collapses down to being 1 minus 1/4. So we start to notice a pattern. S1 is 1 minus 1/2. S2 can be rewritten as 1 minus 1/3. S3 can be rewritten as 1 minus 1/4. If we continue in this fashion, we can write out the sum for Sn. We'll notice again that we get lots of cancellation of terms, and we end up with Sn equaling 1 minus 1 over n plus 1. Now remember, the way we formally defined the convergence of a series back at the beginning of chapter 11 was that if we can find a formula for this sequence of partial sums, if we look at the limit as n goes to infinity, if we get a finite value, then our series will converge to that value. In particular, here when n goes to infinity, we end up getting 1. Therefore, our series that we've been looking at from multiple perspectives, where k goes from 2 to infinity of 1 over k times k minus 1, is just equal to 1 because that is the limit of the sequence of partial sums. So just as a quick summary, we've looked at the same series by looking at it from 5 different ways: the nth term test, the comparison test, the integral test, the ratio test, and looking at the sequence of partial sums. And we could see that the comparison test, the integral test, and looking at the sequence of partial sums were all methods that we could use to show the series converged, but the most revealing method was when we used the sequence of partial sums, because we could actually find the true value that the series converges to. And that concludes our discussion of this infinite series. Thank you.